Hey folks, is this working? Yes it is. Okay, thank goodness. Alright, so what you're gonna see here is that the problem 18, you're specifically asked to get the IR and Raman uh, peaks. And if you try to do it according to your book, you have to do some pretty complicated matricic linear algebra, which is matrix calculations and a bit beyond the math that you're expected to have at this moment, or actually need for the degree. so, um, what I would recommend and why I posted this actually is you may have noticed that I posted a link to Hertzberg, which is the spectroscopy book from the 50s, where they've solved out how to get each of the different point groups, different symmetries for the spectroscopy. Right here is the different symmetries. Right here is the, for example, the first A for the NH3. If you were to go ahead and go and do the point group for that, it's trigonal planar, not trigonal planar, excuse me, trigonal pyramidal. And what you would see is that you'd end up with C3V. And so these right here are some fairly simple calculations. If you go up to this page here and take note of the page number 134, you'll see that there's a little guide on how to actually figure these out. Actually, the like 10 pages before, not 10 pages, about 5 pages actually before this, shows you an example on how to do this in case you're curious and you'd like to learn this, which anybody going into any type of vibrational spectroscopy especially, but microwave also, any type of spectroscopy, it's a good idea to go ahead and have some idea of how to do this. It's one of those skills that really can fix problems when they pop up. Anyways, I went ahead and took a picture of this so you'll have it over here whenever I do this problem, because I'm going to need the little part right here. Make my life easy because we're not on the first table, we're on this one right here for the NH3. And so what you would have seen when you did the flow chart, of course, is that NH3 has a rotational axis. So we got our C3, right? And then we have vertical planes that goes through the hydrogen and nitrogen on the 3 different sides for it. And so you got those 3 hydrogens that come out down in a pyramidal structure that is a triangle. And then you have planes of symmetry going through, hydrogen and nitrogen on each of those sides, which is the 3 planes of symmetry. Okay, and so what you'll end up seeing here is whenever you do these problems, there's a reason that this part is the first part. And you'll recognize that N from another calculation. That's the degrees of freedom calculation. So you may recognize the 3N, which is the degrees of freedom. And those are degrees of freedom as in there's 3 dimensions. So every single atom in the molecule can go 3 different directions and change things. Now, those changes, when you do them, sometimes they all line up, and that would be what's called a translation. And that is that -3, so you remember that there's an n 3n minus 6 for the number of vibrational modes, the number of unique peaks that would be from this molecule. And the -3 of that is actually the number of translations, i.e. it literally moving in space. And then the 3 more of those are rotations. And so for a nonlinear molecule, we do 3n minus 6, and that's your number of total vibrational modes. This is that same n number that you would plug into that. So it's just the number of atoms. And what you're seeing here is that because of the limitations of this point group and the symmetries within it, these calculations right here has to be true. For example, there have to be 3 atoms on planes of symmetry. So that's what this one says right here actually, is there has to be, if there's something on a plane of symmetry that's doing this C3V, then there has to be 3 atoms that are not on the axes on the plane of symmetry, and that would have to be true. Alternatively, you could have 6 things that are not on any of those, And that would give you 6 right there, but that's a more complex, larger molecule. And so this set of conditions always has to be true if you fulfill the symmetry elements for C3V. These always have to add up. It's kind of a ingenious solving down of this to a more humanistic approach to looking at things. Okay, so let's go ahead and do it. I'm probably going to need to bring this up, actually. There we go. Yeah, I looked this up earlier, and I forgot to actually bring it up in the figure. So, I actually found a nice digital thing that I could use because I wasn't going to be able to show my hands in the model kits, right, on this video. This took forever. Oh my god. This was not the right subject to try doing a video on. But we're doing it. So this right here is your trigonal pyramidal NH3, of course, and it's has the lone pair up here, which is causing these things to get pushed down. These right here are your symmetry elements. There's your C3. Notice there's actually 2 of them. I think this web page, yes it does, which is the 120 degree rotations you can make as well. So you can actually do this in 120 degree rotations as well. It's the same axis though. And that's your principal axis, and that means that this up here, which is the C3, right, going through here, as if we're pointing through there with our finger. That right there actually has the is the Z, and so we would set that as Z, and then we're going to go through these different symmetries, and we're going to figure out how many there are of each. Keep in mind that whenever we do this, we have to add together right here to give 4, which is the number of atoms. Okay, so automatically we know we don't even have to do this M here. That's just not possible. Okay, in fact, there can only be 1 here and 1 here to give us 4, right? So I'm going to still show you how to do it, because some of the other problems you'll actually have to do it. But if you get a small enough atoms, there's actually a very limited number of combinations of these this formula here that would be able to actually give you the answer. In this case, there's only 1. So yeah. Yeah. Okay. So we go through, and so M would always be the number of sets of equivalent nuclei, not on any element of symmetry. Well, that's not true for any of these, is it? You have the plane of symmetry, it goes through everything here, and so you don't have anything that's not on any element of symmetry. Notice the terminology here, equivalent nuclei. The hydrogens here would be equivalent nuclei. They're the same type of nuclei, right? Nitrogen then would be another set of equivalent nuclei. Even though it's only 1, it still makes a set of 1, right? Okay, and so M0 is going to be the number of nuclei on all symmetry elements present. Well, we actually look at nitrogen here, and we see it's on the axis. We see that's also on the planes of symmetry. All 3 of them go through that. And so what we see here is nitrogen fulfills that condition. And so that is your M0. Again, is the number of nuclei this time. It's not sets, but we only have 1 anyway, so it doesn't matter. So we do a 3 times 1 here, and so that's 3 of this numbering here. I'm sorry, a 1 right here. We just put that in, and that's plus 1 now. So we've taken care of 1 of the 4. As you can tell, it's going to be MV has 1. By the way, whenever you do these problems, keep in mind it's just a linear equation. So you can actually, if you're not quite sure, you can actually use the math you already know to go, oh, it has to be this one. It's faster and it has to be true, so Okay, symmetry. There's MXY, MXZ, MYZ, and you can kind of guess that these are going to be the numbers of sets of nuclei that are going to be on your XY, XZ, and YZ planes. So remember that in this case right here, this nitrogen, first off, we don't have that symmetry element, so I don't want to do that for this C3V. But for example, this nitrogen right here would be on any of those, it would be on several of those planes, right? Because it's in the z-axis, and so it's always in the z, right? Because it's right where the plane has to go through. And so let's say that this one lined up with one of the y-axes, okay? So you set that to the y-axis, and so your zy plane would be this right here then. And so that would be these two, and we would then go number of sets of nuclei lying on those planes, so that's 1, 2 sets of nuclei lying on that plane. And then you wouldn't have probably anything on your, you don't have any other planes, so it's just not an issue for the other ones. So I can't really demonstrate those. But if you had like a XZ plane or a Y X plane, which would be a flat plane like you'd have for something that's like a a 6-membered ring, like a benzene ring, would have a nice flat plane, right? That would be perpendicular to its rotational axis, its principal axis. Okay, and so the next one we go through here is the M2. That's the number of sets of nuclei on a twofold axis, but not at the point of intersect with another element of symmetry. So for example, this one's at a point of intersect with another symmetry element, so that one would never be an issue. We don't actually have a C2 here, but hopefully that helps if you run into that later. Okay. And then we have the M2X, M2Y, M2Z. These are the number of sets of nuclei lying on the X, Y, or Z axis if they are twofold axes. So again, if we had a twofold axis, it would be something like the nitrogen here, which is in your C3 axis, right? So the axis goes through it. If we had like a trigonal planar one, these hydrogens here would be on C2 axis. So these would be those that we were just talking about, except they'd have the planes also going through them in this case. Keep in mind that they have to not be on all of them. For example, nitrogen here would not fulfill that. So if we had trigonal planar here, it would not be in these M2X, M2Ys. MH is the number of sets of nuclei on a plane. Now keep in mind this is just for the H1. There's an MV as well, which we see over here. That'd be vertical plane. MH horizontal plane, MV vertical plane. But cannot be on the axis perpendicular to this plane. So remember, your C3 axis here is perpendicular to your horizontal, right? The MV, on the other hand, is going to end up being parallel to the C3 axis. So what we're going to end up having here is that, oh, it doesn't have the MV in here. Anyways, for the MV, it ends up needing to not be, oh, okay. Anyways, I'm not going to try to find it. I'm just going to tell you guys what it is, so you don't have to deal with it. So, for the MV, what we'd end up seeing is that the MV needs to, again, not align with its axis. In the case of an MV, the principal axis is never perpendicular to it. It's always parallel. It's always part of the plane. And so what we end up seeing here is, again, the nitrogen has the axis through it. The hydrogens do not have the axis through it. And so they're only on the planes of symmetry, not with the axis through it. And so we have an equivalent set of nuclei, which are the hydrogens. And that's 1. And so it's going to be 3 times 1 plus 1, which is 4. So then we go through here. Now, if we look at our character tables, let's put my hand over here. There we go. Okay. If we look at our character table here for the C3V, what we notice here is we have these are rotational modes, of course. These are the translations, but these are also what give you your infrared modes. Okay, and so the Z, X, and Y's here, these are infrared active. So any of these ones that we come up with as being bands in those modes, these are going to be infrared active. They're also Raman active in this case. The quadratics here are the ones that tell you if they're Raman active. So again, it's A1 and E that are Raman active and IR active in this case. And the A2 really is only rotationally active. There's rotational elements that violate that change that symmetry. Which you can see just directly corresponds to a change in the planes, actually, that negative change in plane. Okay, and so we go through the C3V here, and we do A1 and E is the ones we're going to have to do. And remember, we ended up with 1 MV and 1 MO. So we go ahead and plug those in. 1 MV, that gives us 2, plus 1 from this one, minus 1, so that's just 2. So there are 2 infrared and Raman active modes that are A1. Now, these A1s are actually quite important because that gives them certain symmetries. For example, if we were to do something like a gas infrared, so it's a gas phase infrared, you would actually see different bands depending on the symmetries, and they'd have actually different parts of the band show up, and you can very clearly tell the difference between them. You can actually also separate them from polarizability. So, for example, you can put you can polarize the light coming in and going out on the Raman. Usually the light is polarized already coming in, but you can polarize the light with a just polarizer like your sunglasses of the light coming out of a Raman. And what you would end up seeing is that different symmetries would actually have their intensities greatly reduced because they would polarize light depending on your symmetry. Okay, and so we ended up with 2 A1s that are infrared and Raman active. We go over to the E, which is the other one that's infrared and Raman active. We go ahead and substitute our numbers in again, and we see again we have 3 times 1 plus 1, so that gives us 4, minus 2, that gives us 2, and so we have 2 infrared and Raman active modes for the E. And that's how you go ahead and do that very quickly. Notice that if I didn't take all the time to explain, this would have taken me a couple minutes, if even that. And so this problem is actually quite trivial as long as you use these tables. You will note that these tables go up to very high symmetries, which is what just causes most inorganic chemists who would do it the inorganic chemistry way to figure out those modes to just blow their minds that this actually can be reduced down to very simple linear calculations. By the way, there's actually explanations too to each of these things in tables that are later on. So this is like 21, 22, and it actually breaks it back out. Let's see if I can actually get down to one. No, they're too far away. It actually breaks it out to a bit more complexity. So you can then go back out to the more complex from this very easy, less complex way of doing this. And so it's kind of funny, you can sidestep the complexity of having to actually try to figure it mathematically out, very complex, long calculations that take hours and hours. You can do it in a couple of minutes and then get all the same information because these point groups. So, yeah. Anyways, so this is how I actually expect you guys to be able to do this, and this is why I kept this problem in here, because I specifically wanted you all to use this, and that's why I linked this document and everything else. And I even pointed back to it in the solve problems, by the way. Alright, you all have a great day, and take care. Let me know if this helped at all, or if you're still confused. Okay, bye-bye.